Hello, calculus fans. Let's suppose we got a large warehouse and there are fans inside that move the air around in the warehouse. So we can take any point in the warehouse and say that the air is moving at some speed and in some direction. Or, to be more precise, using the language that we've concocted in this class, we'll say that the air moves with a particular velocity. We'll associate every point in space with a velocity vector of the air movement. This is an example of a velocity vector field. And the term that we're really trying to introduce here is vector field. There's another type of vector field called a force field that associates a force vector with each point in a region. We'll get to talking about force fields later. So in general, a vector field is a function whose domain is a set of points in R2 or R3 and whose range is a set of vectors. We're typically going to keep the range to be the same dimension. So if the domain is a set of points in R2, then the output will be a range of two-dimensional vectors. Let's make a definition to say that if we have a set D in R2, that a vector field on R2 is a function that assigns to each point xy in D a two-dimensional vector, and we'll call that f of xy. Notice that I'm putting a vector symbol over the f. Probably the best way to visualize a vector field is to draw the arrow representing the vector f of xy starting at the point xy. Now we can't do this for every single point xy, but we can get a reasonable impression of the vector field by doing it for a few points in D. Here's a picture. So we've picked some points and we've created the vector at that point. This is an example of a vector field. Now, f of xy is a two-dimensional vector, so that means we can write it in terms of its component functions, p and q, like this. We can say that f of xy is equal to p of xyi plus q of xyj. Here, p and q are not vector functions, they're scalar functions. Or we could just write pi plus qj for short. Keep in mind, p and q are scalar functions of two variables. Its output is a scalar. And we'll sometimes call these scalar fields just to distinguish them from vector fields. Note that we can also create three-dimensional vector fields. So as a definition, we'll now pick a subset of R3. So now a vector field on R3 is a function that assigns to each point xyz in E a three-dimensional vector, f of xyz. Let's look at an example of a vector field on R3. Harder to visualize, but here you have three-dimensional space, and these are intended to appear to be three-dimensional vectors. Just as in the two-dimensional case, in 3 dimensions, we can express a vector field in terms of its component functions p, q, and r, like this. And finally, just as we talked about with vector functions in a previous chapter, we can talk about continuity of vector fields and say that a vector field is continuous if and only if its component functions are continuous. Okay, that's all for now.